Hello, and welcome to the fourth presentation I gave for my physics club, Stars and What Did They Reveal? This video is split into two sections, one with a voiceover I'm doing right now, and one with a live recording that I've done a couple of weeks ago. Without further ado, let's go on with it. So what is in this session? Well, we have three sections and a conclusion. Section 1, what are stars? Section 2, Astronomical Spectroscopy. And Section 3, Dating the Universe. Finally, we have a conclusion and a puzzle. So Section 1, what are stars? What are the different forces that act within a star? And how are these forces created? So, what is a star? Well, I'll let Pass Me tell you what it is.
A definition is that it's an astronomical object containing a sphere of plasma, and plasma is a charged gas. Now, a star is held together by two conflicting forces. We have gravity, which is trying to contract the star into a single point. And opposing that, we have pressure that tries to expand the star away from that point. So we have a diagram here of these conflicting forces trying to squish and stretch the star, and the star is basically like a constant fight between these two, which the star is normally in something called a hydrostatic equilibrium. So let's talk about one force, gravity. So all matter attracts each other via the force of gravity. That's very well known. So in stars, the plasma is attracted towards the center of the star, which is called the center of gravity, which is normally at the center of mass, and it's compressed the star. So looking at each individual particles, as they are attracted to the center of the star, it transfers energy, and more specifically, it transfers gravitational potential energy of that particle into kinetic energy of that particle, falling towards the center. Now, if we presume this plasma acts as an ideal gas, so basically what that means is that we kind of simplify down this gas model we make some assumptions, and we simplify it down so we can actually work out some physics about it. If we presume it's an ideal gas, temperature is proportional to the kinetic energy of those particles. So here we have T is proportional to KE. Now, as plasma is gaining this kinetic energy by falling towards the star, it heats up. So both of them will increase. And at some point, this temperature becomes so great that it allows the creation of pressure to act on the star. So let's go on to the second force, which is pressure. So the plasma being compressed by gravity gets very, very hot. And if you can have a quick guess on how hot it can get.
About 5,000 degrees Celsius?
Well, it gets up to 15 million degrees by this. And at this temperature, nuclear fusion in the stars occur. Now, this is because the nuclei have enough speed to overcome something known as the Coulomb barrier, which is this like little barrier here, which repels them normally. And more detail on this can be found in my previous talk once I get it up on my YouTube channel, if you're interested more about nuclear fusion. So, nuclear fusion produces electromagnetic radiation as one of its products. And electromagnetic radiation can exert a pressure. Now, let's go on to that a bit. How can a wave exert pressure if it has no mass? So, as I said, electromagnetic radiation can act as a wave, but it can also act as a particle. And this is because of the wave-particle duality at the quantum level. We discovered this back with Max Planck and Albert Einstein finding out the photoelectric effects. Now, electromagnetic radiation can be expressed as photons, which is the particle form of it. And these photons have momentum, but they have no mass. So how can they have momentum? Well, it's given by this equation here. We have momentum here is equal to h divided by the wavelength. So it's Planck's constant, which is a number Planck worked out, which is 6.63 times 10 to the minus 34 joules per hertz. And we divide that by the photon's wavelength, and we can find out the momentum of this photon, which is a bit weird since it has no mass, so we can't use P equals mv. So when these momentum collide with the plasma particles, it can transfer momentum over to the plasma. In comes a photon with some momentum. It bumps into it, and in this example, we transfer all of this momentum gets transferred to this plasma particle, and it goes off that way with that momentum. And this creates pressure. So that's how the force of pressure in stars is created, because of the radiation emitted by nuclear fusion. Now, talking about nuclear fusion, there are two. Talking about nuclear fusion, stars convert hydrogen in their core to helium, and that's by nuclear fusion. That's basically the process of what a star goes under. And there's two different fusion chains that a star can use to create helium. So one of the chains is called the proton-proton chain, and the other one is called the carbon-nitrogen-oxygen chain. I know that sounds a bit weird, but I'm going to have some comparisons here. So the proton-proton chain is dominant in stars that are around the mass of our sun and smaller. So that's how they create their pressure. Well, the carbon-nitrogen-oxygen chain is dominant in stars bigger than our sun. Now, the proton-proton chain needs a lower temperature in order to use, and if you can guess where this comparison is going, the carbon-nitrogen-oxygen chain needs a higher temperature to use. And a quirk between these two is the speeds. The proton-proton chain is actually pretty slow, at least with the first reaction, which I'll detail on later. This is because it involves the weak nuclear force in order to start the chain off, which is, well, very slow. But the carbon-nitrogen-oxygen chain does not use this force, so it can go faster and produce more energy. And a side effect is that bigger stars have a lower lifespan than smaller stars, and that's a reason why. So, more in depth on each chain. So let's start off with the proton-proton chain. There are three reactions in the proton-proton chain. So, the first one is this. We start off with a proton, or in this case, a hydrogen nuclei, and it smashes against another hydrogen nuclei. And this results in the formation of deuterium. So we have a proton here, and we also have a neutron. And that's because one of these protons here, when they combine together, just decays into the neutron and emits it's beta plus. So if you wanted to know the actual equation between here, we have two hydrogens and combine into deuterium, and then we have a positron and a that one I forgot the name of. Neutrino, yeah. Now, the second step in the reaction is this. We take that deuterium and we smash it against another proton. And in this time, we get tritium, which that proton becomes a neutron, and it's, I forgot to do the decay, but it smashes together and also emits a bit of gamma radiation. Now we need to do those two steps another time before we get onto the final step. So we take two tritium atoms and we fuse them together, and we get helium and two protons. So that's the equation here. And a fact is that 0.7% of the mass, so if we take the mass of these 4 protons, because we convert these 4 protons into helium, if you work out the mass difference here, there's a 0.7% difference in this, and this is because that mass has been converted into energy, and there's a lot of energy because it's nuclear fusion, and that's because of E equals mc squared. Mass is related to energy. Now we're going to go on to the second chain, which is the carbon, nitrogen, oxygen chain. And here's a general overview of it, but let's just label each different step and we'll go through that. So we start off here at 1. So carbon 12, so this nucleus right here, fuses with hydrogen, so hydrogen and carbon, to create nitrogen 13. And you can see that it's emitted a photon here coming out, a bit of energy that's coming out of it. So our second step is that nitrogen 13 is quite radioactive, and it decays into carbon 13 to become more stable. And this emits a positron and a neutrino, and that comes out. Then we combine our carbon 13 with hydrogen again to create nitrogen 14, and this is a stable form of nitrogen, so it doesn't decay. So our fourth step is that nitrogen 14 fuses with oxygen and creates nitrogen 14 fuses with hydrogen and creates oxygen 15, if I said it right. And that's why we named this the carbon, nitrogen, oxygen cycle, because it uses those 3 elements. Now oxygen 15 is radioactive, so it decays into nitrogen 15 to become more stable. And then finally, nitrogen 13 fuses with hydrogen, and then this releases a helium atom and decays into carbon 12. And so the cycle starts again. We use carbon 12 and go along here and release, and this converts 1, 2, 3, 4 hydrogens into helium. So let's get on to the second section. Yeah, let's just move on. So what is this? How does electromagnetic radiation interact with waves? With matter, sorry, that's a typo there. What details can we pick from stars? Let's move on. So what is this? Well, this is the usage of spectroscopy to measure the spectrum of incoming radiation from stars. So, as you would know, the sun emits light. So we can take that light, and even the light we can't see, we still take that, and we analyse the spectrum of that to determine key features from that. And spectroscopy is the study of interaction between electromagnetic radiation and matter. That's why I said type there. So this is split into X-ray, optical, and radio. And this is because of varying levels of different electromagnetic radiation that's absorbed by our atmosphere. As you can see, X-rays and anything kind of UV and less, so UV, X-rays and gamma, is absorbed by our atmosphere. So we have to use satellites to observe them. But visible light and radio waves, we can observe these on Earth quite easily. That's why we have 3 different branches of this. So what's so special about electromagnetic waves? So let's say we have our telescope here. Okay, this is a radio telescope. Now we're going to point it at a star, and we pick up some radiation from a distant star. Now, this incoming radiation from a star must have interacted with the photosphere of that star, which is a layer of matter around a star which photons have to pass through before escaping the star. So if the photons are generated here, they have to go through this bit of gas to come out to be detected by us. So let's have balloon our view on this. So stars release different wavelengths of radiation. So we have so we're going to categorize this as red, green, and blue. Now, when radiation interacts specifically with a gas, some things can happen with that radiation. So one of the things that can happen is that specific wavelengths pass through that gas, otherwise known as transmit through that gas. So this green wave right here, it passed through the helium quite easily. However, some wavelengths can be reflected by an element. So our blue wave here just got bounced off by helium gas. And then finally, some wavelengths can be absorbed by this element. So you see this as red, this interacts with here and is absorbed by the helium. But also, if you can absorb if a body can absorb a specific wavelength, then it can also emit that wavelength. And when this helium gas is heated up, it can emit that wavelength. So, what does this mean? What do we actually see? So, in comes our radiation from a star, and this is made up of different wavelengths. Then we can use something called a spectroscope, or in this example, a prism. Since I'm giving the example of optical light, and a prism, if you ever put some light through a prism, then you know what's about to happen. Is that this light is split into its different wavelengths that it was made out of. So, what do we see? Well, we can see something like this. We observe a spectrum of light, but then there's bits like here or here that's just missing in wavelength. And this is called an absorption spectrum. the missing parts of the spectrum here have been absorbed by something. Or we can observe something like this, where we only get specific wavelengths through. So in this case, red, green, blue, and purple. And we're emitting everything else. And this is called an emission spectrum, because these are wavelengths that have been emitted by a gas somewhere. So, just on these two things, looking at absorption and emission spectrums alone, we can detail so many different things about stars. So, detail number 1, chemical composition. The spectra of stars can be catalogued and be used to determine the chemical composition of that star. So we've actually seen, we have observed the optical spectra of several stars, including our own sun. And if you, this is known as the barcode of the sun, which is basically its optical absorption spectrum. And you can see it's missing different parts of this continuous spectrum, and that's because of some specific wavelengths have been absorbed by the elements inside the sun. So by matching absorption lines to elements tested in labs, because we can heat up, let's say, that's a bad example, iron. We can heat that up and then pass light through it and see what wavelengths are absorbed by iron. And we can match this with absorption spectra on different stars, and we can say, oh, that star contains iron because because these XYZ wavelengths are missing. And the fact is that helium was discovered 27 years on the sun in the year 1968 from using this before it was ever found on Earth. So this method has actually predicted an element before its formal discovery. So another detail we can find out is density. So yeah, we can use this method to tell us how dense a star is. So the denser a star, the more collisions radiation will have in the photosphere. So if it was less dense, we have less particles in that photosphere. If it's more, then we have more. And this will lead to the absorption lines view to become blurred as the density of the star increases. So we have a blue giant here, that's quite massive, and we have a white dwarf, which is the size of the Earth. And while they differ in mass, they basically kind of emit the same wavelengths of light. But you can see here that while the blue giant, which is less dense, have clear lines saying, oh, this wavelength is missing, this wavelength is missing. We can see in the white dwarf these have become blurred, so it's not as clearly defined. And detail number 3 is the temperature of the star. You can see here we have the graph. So we treat star, I haven't said this, but we presume we treat stars as black bodies which can emit all wavelengths of radiation. That's why we can use all of this before, because we say that they emit every wavelength of light, but some wavelengths are absorbed. So William Wing derived that a temperature of a black body is inversely proportional to the wavelength with the greatest intensity. And this comes up as T equals 0.00289 divided by the wavelength. So if we split this wavelength with greatest intensity, I forgot to say that. So if we split the starlight into its spectra, and we see like, oh, this wavelength right here has the greatest intensity, we can say that we use this formula here with that wavelength, and we can find out the temperature of the star. And you can see here that if we have our wavelength here, and this is supposed to be intensity, that's called flux, and we can see that it kind of curves like this. This is our peak. This is our wavelength that's the most intense, and we can say that using this formula we find that a red star has a temperature of around 4,000 Kelvin. So section 3, the universe. What methods do we use to date stars? And how can stars help us find the age of ancient life? I don't think you know where, well, Henry might know where this second link might come in, but let's go on. So why would we want to measure the age of stars? Well, one of them is we can compare different values for the age of the universe using different methods. So we can get the age of the universe from measuring stars, or we can get the age of the universe from measuring the expansion of the universe. And we can say, oh, these values here, they're a bit different. What's gone wrong here and stuff, and we can try and find a more precise date for the age of the universe. Now, more local, the age of a galaxy. So we've dated stars in the Milky Way to find out the age of it. And we can also, even more local, we can find what point a star is into its life cycle. So let's go on to one of the methods. We can determine the age of a cluster of stars using this method here. So astronomers can assume that stars were born in the same. We can assume that stars that were born in the same stellar nursery, which is like a type of gas cloud that is suitable for star formation, were born roughly at the same time. Then we can measure the star's luminosity and temperature within the cluster, using the temperature method we just discussed. And astronomers can then plot a Hertzsprung-Russell diagram, and we can find some interesting things. So let's set up our axes with temperature and luminosity, and let's start plotting. So we go along here and we find some. It's kind of trend, following the trend right here. It's kind of going up like that, and these stars at the bottom here are called main sequence stars. And main sequence stars are stars that are in the longest cycle of their existence, but converting hydrogen into helium. And then we might find that some stars do this. They start to go off that way. And these are red giants. And basically these stars have ended their main sequence stars. They've stopped fusing hydrogen into helium, and they've started converting heavier elements, so helium into lithium and so on, until you get to iron, and then it explodes. Now, what astronomers are interested is in this section right here. These are stars that are at the end of their roughly at the end of their main sequence lives. And this is important because we know how long a star can spend in their main sequence. It's roughly 90% of their lifetime. So looking at these stars, say they're about to end their main sequence, we can actually use models to work backwards, and we can find the age of the entire cluster, and thus the age of each of those stars. Of course, this is assuming that they were born at the same time. So, determining the age of a singular star. You can't use a Hertzsprung-Russell diagram on a singular star, because, you need multiple. If you only have one point, you don't know if it's too old or too young, or you don't really know where. But luckily, there are two different methods to determine the age of a star on its own, and let's go over this. So method number 1, the rotation of a star. So we spotted that young stars appear to be spinning faster than older stars. Now, how do we measure the rotation on this? Well, if you look at a point, if we observe the spectrum of the star, then since it's coming, radiation's coming, moving is in its points. So if we have a star here, we have a point that's moving like this, and we have an observer here, it seems like the radiation's coming towards and further away from us, like going towards us and further away from us. And this invokes a Doppler effect, which is what we use to discover that the universe was expanding. So if we have a normal star here that's stationary, and we have a star here that's rotating, then if we analyse the wavelengths, then we can find that while this star here has is missing this wavelength right here in the middle, if we're using a similar star, we find that we're missing even more, because that missing wavelength has been shifted, red shifted and blue shifted. So we can say that, that star's rotating. So astronomers have worked out that the age of a star is equal to 1 over the rotation rate squared. It's a nice little formula. However, stars older than our sun have been discovered to stop slowing down. So unfortunately, this method becomes a bit unreliable if we measure stars older than our sun. And that comes on to our second method, called astroseismology. Now, what on earth is that? Well, stars can produce vibrations itself inside, and this is due to fluctuations in the temperature causing waves. These vibrations cause waves to ripple inside the star, and we can see that as periodic changes within the star's luminosity. So, if we have a star here, and we have a hydrogen and helium core, and we have some waves that ripple like this, kind of like seismic waves in the Earth. Then what we see is this. If we put luminosity in time, we see that there's a periodic change in the luminosity, like this, due to the waves. And by observing this, astronomers can work out the internal structure of the star. And then, knowing this, we can work out how old a star is. So we say that, this star here has 20% helium and 80% hydrogen in its core. It would say, it's 1 billion years old, or something like that. Now we're actually going pretty low, local, as in on this planet, using carbon dating. So on Earth, there are several methods to try dating ancient life, and one of them is carbon dating. So carbon dating is where you use carbon-14, which is a radioactive isotope of carbon, to try to find its age. And that plants, anything organic has carbon-14 in it. So, how is this related to stars at all? I mean, this seems like two completely different fields. Well, you'll find out that they're related due to the natural production of carbon-14 itself. So carbon-14 is produced from nitrogen-14 reacting with a neutron in the outer atmosphere. So we have our equation here. We have an incoming neutron. We have some nitrogen, and it reacts to create carbon-14 and a proton. So neutrons have a decay into protons after 50 minutes. So where did this neutron come from? Well, it's in the upper atmosphere. The neutron could be a secondary cosmic ray. So here comes our link. So secondary cosmic rays come from primary cosmic rays interacting with matter. And this basically causes nuclei to undergo spirangulation. It essentially just explodes the nucleus out. Although it's not like fission where you can continue this chain reaction. So we have some primary cosmic rays coming in, and it explodes it, and it releases a neutron. And this might be this neutron over here that we must have to produce carbon-14. So where does this primary cosmic ray come from? And the primary cosmic rays come from stars, like from events of solar affairs, from our own sun to distant supernovae. And that's actually how carbon dating is related to stars. If we didn't have stars, then we couldn't use carbon-14 as a method of dating life on Earth. That's an interesting link you probably would have never guessed, except Henry, because he's learned the syllabus. So, wrapping everything up, we have learned about the forces that dominate in a star and how they're created. So, how gravity conflicts with pressure and how that pressure is created from nuclear fusion. And then we discussed how we can find the details about a star, like its chemical composition or temperature using spectroscopy. I'm not. And then finally, we used how stars can date the entire universe from galactic structures down to me or you in a few thousand years. So, let's wrap up last session's puzzle. This is the pole runner paradox, as I like to call it. And this is due to general relativity. So we have a pole runner here that's moving near the speed of light. And what happens is that when you move near the speed of light, from observers, you seem to contract, to squish up. So for you, this pole was measured the same length as the barn, but since the pole runner is moving near the speed of light, the pole's now shorter than the barn. So you can close both doors and trap them in. However, speed is relative. So as I could say, I'm moving at x speed. We can also say the world is moving towards me at x speed. So this causes the opposite effect, where the barn contracts and now the pole cannot fit in the barn. However, both scenarios are correct. So what is going on here? So here's the solution. Travelling at the speed of light not only distorts space, so if this ruler is travelling near the speed of light, it would become like that, squish, but also time. So our poor stopwatch here it's not working quite as well. So the barn doors closes simultaneously for you. We said that in the problem. But who says that the same thing happens to the pole runner? Well, since time distorts for him, because he's travelling near the speed of light, why would we say that time flows for him as it flows for you? So let's play this scenario out. We have a pole runner approaching the barn. And while for you close the door simultaneously, this is what happens from the point of view of the pole runner. So he comes in, and he gets here, and the front of the pole is just about to touch the back door. And then it closes. And then it opens again, and it didn't hit it, so the pole runner continues on. And then the back part of the pole passes through the front door, and then that door closes and opens, and it continues on. So that explains why the pole cannot fit in the barn, but also fit in the barn at the same time, because events transpiring for you are different from events transpiring in the pole runner. So puzzle number 4, and that is the DeLorean. So, the grandfather paradox, and generally time traveling in general. Let's have a quick rundown of this. You might have heard the grandfather paradox before, but let's try this. Let's say one day you find a time traveling machine, or invent one. I don't know. If you invent one, that would be pretty incredible. And now you say, I'm gonna go kill my grandfather for whatever reason. I'm not gonna dwell into it. So you go back in time and you go kill your poor grandfather, although he will be quite young then. But here's where the paradox lies on. If your grandpa has never met your grandma, let's do this. If your grandpa has never met your grandma, then your parents don't exist, and therefore you shouldn't exist. So how can you go back in time to kill your grandpa? But there's more wrong with this, and this is because time traveling, at least in that form, breaks physics. So the universe only has a finite amount of energy, and that's because of the conservation of energy. Energy is not created or destroyed, it's only transferred. So let's say you have a little family here, back in time. We can say that the total energy of this family, or the general universe here, is this, it's quite full. But you coming back in time essentially adds more energy out of nowhere for the universe. So this breaks off, and then we have the energy of you here, but that's more than what the energy of the universe had beforehand. So you have just violated the conservation of energy, which is a big no-no. So how do you time travel back into the past and enact your scheme? And I'm not accepting you can't time travel. You gotta think of a solution here, because if the answer was it was logically impossible, that would be quite a dull answer. And that's the end.
Yay.